So in the last lecture, we learned about resistors, resistivity, and currents. So now what I want to do is talk about how we can connect resistors up to batteries and make circuits. And then what we would like to do is to solve the properties of the circuit. So for instance, how much current is flowing through a given resistor. If we have a bunch of different resistors, what is the voltage drop across resistors? And basically, being able to do this is the backbone of our modern electronics, right? In our telephones, in our smartphones, we have lots of little integrated circuits that have millions of these resistors and capacitors inside. So in the next couple lectures, we'll talk about how to solve the properties of circuits. All right. So I'm going to start with a pretty simple example. And so we're just going to consider a circuit that I've drawn here on the left, which is just a single battery, which is denoted by this sort of symbol where there's a long bar on the top and a shorter bar on the bottom. Okay. And then it's hooked up to a resistor over here on the right. And we want to know how much current is flowing through this resistor. So again, I just want to review some basic symbols. So again, for the battery, we have a long bar and a short bar. And what the long bar represents is the long bar is at a higher voltage than the short bar. Okay, so for instance, if I say this battery has some voltage, in this case E, so let's say if it's a AA battery, that's 1.5 volts. Okay, and the long bar is basically at 1.5 volts higher voltage than the short bar. So if you look at your battery, there's a plus and a minus. So basically this would be the plus end. It would be plus, if it was a AA battery, 1.5 volts higher than the negative or short end. Okay. Then you have this resistor, right? And we talked about, a block of conductor in the earlier lecture, and the electric field through it, and the current that flows through it, and we could define a quantity called the resistance of that chunk of conductor. And so we just symbolize that by this sort of squiggly symbol here. And then we have these just lines. The lines we represent as are basically ideal wires. And in the sense that this wire we're going to consider, for simplicity's sake, as having absolutely no resistance, okay? And we learned that actually all metals, in fact, have some resistance, unless, for instance, it's a material called a superconductor. But really, all metals have some resistance. But you can imagine that it's made of some material that has a very, very low resistance, so low that we can neglect it, okay? And there's no resistance. This wire has no resistance, and it has no voltage drop across it. All right, so now what we want to do is we want to solve, let's say, how much current is flowing through this resistor. And so what we're going to do is we're going to employ a couple of laws that we use for solving the properties of circuits, and these are called Kirchhoff's laws, okay? It's written up here, so Kirchhoff's laws. And there's two of them. There's a voltage law, and there's a current law. So I'm just going to write these down now. So as I've just written down here, Kirchhoff's voltage law states that the voltage around a closed loop is zero. And mathematically, what you can express that as is if you sum all the voltages, for instance, from D to A, from A to B, from B to C, and C to D, if you sum those up and they form a closed loop, that voltage is always zero, okay? And if we had a circuit that had multiple loops, then the voltage around each individual loop, they would all be zero, okay? And this is basically, you in fact have already learned this. This is basically the same thing as saying that electric forces are conservative, okay? So if you remember that we had some situation where we had some kind of electric field, and if I basically took a charge and I moved it around in a closed loop in an electric field, basically we said, okay, the work there is zero, basically if you're going to take it from some point and return it. You basically, if you have a charge, you basically do no net work if you move that thing in a loop. If you did, if you did do some net work, then for instance, or let's say there was some network gained by moving it in a loop, then in fact, every time you move it around a loop, you would gain some energy. This thing would be basically like a perpetual motion machine. You could you could basically get an infinite energy amount of energy out just by moving a charge in a loop, and you'd solve all the world's energy problems. So unfortunately, that's actually not the case. And so since electric forces are conservative, that means that if I take a charge, I move it around this loop once, I do no net work. Okay? So the second one is Kirchhoff's current law. So Kirchhoff's current law states that the total amount of current flowing into a point is equal to the total current flowing out. Okay? So for instance, if we consider this point A on the circuit, and we say, well, there's a current flowing into that point, then the current flowing out of that point has to be equal to the amount flowing in. And so this is, again, when we talked about these, incompressible fluids in the context of Gauss's law and also currents through a conductor, right? We said, well, the amount of stuff that flows into one end is the same that flows out, because we don't want to have charge building up at any given point. So if you think of the current as being much like this incompressible fluid, and this circuit as being a bunch of pipes, then on any point in this network, if I pick a point, the amount of fluid flowing into that point should be the exact amount exiting. If that wasn't the case, then we would have a net buildup of fluid, or in this case, a net buildup of charge. And that's not something that we're going to allow. Okay. The one exception to that, which we'll talk about in a couple lectures, is on the plate of a capacitor. Right. So we've learned that on a capacitor can actually store charge. So in certain cases, when you are charging up a capacitor, you can actually have the current flowing into the capacitor kind of start building up on the plates. Okay. We'll talk about that in a couple lectures. All right. So what we've said here, so we're going to use these two laws, the voltage law and the current law. And what we're going to do is we're going to try to solve, let's say, this particular circuit. This is a pretty simple one, but we'll move on to a little bit of a more complicated one in a few minutes. All right. So we'll start with using Kirchhoff's voltage law, right? So we can say, all right, so if we use, I'll call this K1, right? Then we can see that basically the sum of the voltages around this whole loop, right? So I'll call that, so let's take this first one. So V, and that's so this dA, AD means from D to A, plus V from A to B, plus V from B to C, plus V from C to D, right? And we said, so these are all the voltages that comprise this loop. And we're going to say from that first voltage law, this is going to be 0, because electric forces are conservative. You're not going to gain any network from moving anything around in a loop. Okay? Kirchhoff's current law, for this particular problem, it's actually going to be quite simple to employ, because there's no points here where the current branches off and could go into more than one different direction. So, if I think of a current here, and let's say I'm going to define it as going, I guess this is clockwise around the circuit, then basically what it says is that the current, let's say the current in is going to be equal to the current coming out, and that's true at point A, right? So if I look at that point A, the current that's going in this way is the same that's moving to the right, and then it's the same amount of current that goes down from B to C. And the important thing to know is that the amount of current that's flowing out of the battery is going to be the same as is going to be flowing through the resistor. There's no other alternate route this current could take. Okay? So now let's look at these various voltages. Well, if we look at V from A to B, right, basically we can use now Ohm's law. So we learned about Ohm's law in the last lecture, although I guess I didn't actually call it Ohm's law. So Ohm's law states that the voltage drop across a resistor, the voltage across a resistor is equal to the current times its resistance, right? So when we talked about the current that flows through some conductor or some resistor, we found that there was actually a proportionality between the voltage across that resistor and the current that flows through that resistor. And that constant of proportionality we called the resistance. That was due to a bunch of different factors like the geometry of the resistor, its length, its cross-sectional area, and also the properties of the material it was made out of, the resistivity. All right. So we can use Ohm's law, V is equal to IR. So if we're looking at this here, well, we said that the ideal wire has no resistance, right? So if it has no resistance, then the voltage drop, the voltage across a wire, an ideal wire, which we denote just as a straight line, is 0. Okay, so you can see here then we go from A to B or from C to D, because the resistance is 0, V is 0. Even there is some current flowing through it, I, but since R is 0, there will be no voltage through it. Okay, so a current can flow through A to B, but there will be no voltage. All right. So what we're left with when we're trying to solve this particular circuit, right? So we have something here, V from A to D. It's going to be, we don't know. It might be plus or minus. I'll talk a bit more about that in a sec. Plus or minus E, right? And then V from C to B will be basically, if we use Ohm's law, if we said this thing has a resistance R, it'll be, plus or minus IR, right? So we'll say that there's some current I that we want to solve for. We want to know what I is. And let's say we know the resistance already, right? So the resistance is given, it's 100 ohms or whatever you want it to be. All right, so basically then these two terms are 0, so we're left with these two terms, V from A to D, that's going to be plus or minus E. V from B to C is going to be plus or minus IR. And I'll talk now about whether we should pick plus or minus. So let's first talk about going from D to A. Okay, so if we're going from D to A, we're basically going from a lower potential part of the battery to a higher potential part of the battery, right? So we're going from lower voltage to higher voltage, because this is basically how the symbol for the battery is defined, that the higher potential part is this longer bar. So if we're going from a lower potential to a higher potential, we're going to increase our voltage or increase our potential as we go from D to A. This would be like we're climbing uphill, okay? So when we're going from D to A, which is what the order of these symbols mean, the subscript means here, basically this would be a plus, okay? If we're going now from B to C, okay, so if we start here and we end up here, now we need to ask, okay, well, is this going to be a positive or a negative, right? So let's think about this for a second. So the way I've drawn this, the current is moving in a clockwise direct fashion, right? So it's the way I've drawn the current is going from B to C, right? So if we think of this resistor as that chunk of metal with an electric field inside, if the current is flowing from B to C, that means the electric field is also pointing from B to C, right? And we learned that electric fields always point from higher potential to lower potential. So if you think again of the case where we have these two of the parallel plate capacitor, the electric field points from the higher potential plate to the lower potential point, right? So if we go from B to C, we go from a higher potential to a lower potential. So basically, that's a decrease in the potential. So that's going to be a negative sign, okay? So basically what we have then is E is equal, so we have E minus IR is equal to 0. So if I can add IR to both sides, I get E is equal to IR. Or in other words, what we wanted to know in this problem, how much current flows through the resistor, I is just E over R, okay? And this is defined to be in the clockwise direction, so it's a downwards current, okay? So you'll notice one thing I did when I was solving this problem. I just said, well, why don't we define the current to be going in this clockwise direction? What if I made a wrong guess, right? What if I said, what if I actually said, maybe we should have it moving in a counterclockwise direction instead? It turns out that's fine too. If we had done that, then what we would have done is said, well, when we were picking, so then if the current, if we drew the current as flowing from C to B, right, then basically we would have said that, we would have gotten the current to be a negative value when we solve for it, okay? And so if the current ends up being a negative value, then basically what that implies is that the direction you originally picked was not the direction that you thought it was initially. So what you can do when you're solving these circuits is you just define some direction for the current to flow, and you just solve for the current. If it's positive, that means that the current is flowing in the direction you originally indicated. If it's negative, then it's flowing in the opposite direction to what you originally thought. Okay, so what I'm going to do right now is I'm going to write down some sort of tips for how to solve circuits. So these are tips in addition to Kirchhoff's laws. And then after that, we'll do one example of a slightly more difficult circuit, and then that'll be it for today. All right. So I'm going to write down some helpful tips for solving circuits. And these are basically more or less things I've just already said, but just wanted to write it down in a more formal way. Okay, so some helpful tips are that when you go from the short side of the battery to the long side, okay, so this is the negative side and this is the positive side, the voltage will increase. Okay, so as I go, so the voltage change in going from A to B, as drawn here, is plus E. Okay, if I have the exact same setup, so when I say the voltage, in Kirchhoff's voltage law, the voltage around a closed loop is 0. It doesn't matter whether that loop is going clockwise or counterclockwise. So I could have made another loop where I go, around in a counterclockwise way. In this case, we would then be going, let's say, from B to A, and then the voltage drop changing going from B to A. If I was starting from the positive side and going to the negative side of the battery, that would be minus E. Okay, so just remember that. The voltage decreases or drops, so we often say the voltage drop across a resistor, meaning the decrease in the voltage as we move as we go across a resistor. The voltage decreases when we go across a resistor in the direction of the current. Okay, so if I'm going again, so let's imagine I have this situation drawn here. The current is flowing, or let's say I've denoted the current to go from B to A. So in that case, then the change in the voltage when I go from B to A, from top to bottom, is going to be minus IR, right? It's going to be a decrease in the voltage. It's going to be a drop, so it's a negative value. Again, if I have the same situation, but in this case I wanted to go from A to B, right? So here I've inverted the indices here, just like I have here. So if the current is still going down, but my for whatever reason, I'm doing my Kirchhoff loop and I'm going against the current, then that will be then a increase in the voltage, right? And you can always think about that because if you think about, there is some electric field inside this piece of metal that's causing the charge to drift downwards, or the current to drift downwards, then basically if I go opposite that, we know that the current will always drift from a higher potential to a lower potential. So if I'm moving then from A to B, I'm moving kind of against the flow. I'm kind of going uphill. So that's going to be an increase in the potential. All right. And some other tips are that, let's see here, I'll pause this for a sec. So there's a couple more short tips. So the third one is, as I said earlier, when you're starting off solving the circuit, you should initially specify some direction in which you think the current is flowing. All right, just give it your best guess. And it actually doesn't really matter, because at the end of the day, if your answer for the current is a negative value, it just means that the current is flowing in the opposite direction than you initially picked. Okay? So, you just basically give it your best guess, and, the math will tell you in the end whether you picked the right direction or not. And if it's not, then no big deal. You just flip the sign. And the fourth thing is that if you look at a battery, in fact, current can flow through a battery, okay? In reality, it's actually not flowing through the battery. I mean, you have basically, a positive terminal and a negative terminal, and you have basically, for instance, in a let's say lithium-ion battery, you have some charge stored in there that can move from sort of one part of the battery to another. But for the purposes of your circuit diagram, you can really just think of the current as flowing through the battery. The battery does not interrupt the current. Okay, because sometimes if you look at that symbol, it might kind of look like the circuit is broken and you're not allowing any current to flow through, right? If I look at this symbol up here, it looks like it's a break in the circuit. But in fact, you could effectively think as the current is flowing through, all right? Now, a real battery eventually, it won't maintain this voltage difference and won't let current flow through it forever. It'll eventually, the batteries have some sort of finite capacity, some finite amount of energy stored in them, and but for the purposes of this class, we won't worry about that too much. All right, so what I want to do now is I want to solve a slightly harder circuit, and I want to use basically all of Kirchhoff's laws that we've talked about. All right, so here's a slightly more tricky example, right? So now we have a battery, and instead of just having one resistor, we have three, okay? And they're hooked up in some kind of configuration like this, okay? So it's a little bit trickier. You can see there's junctions here where, one resistor is hooked up to basically one and another one, right? So it's a little more tricky. The current can maybe, be diverted into different directions and things like that. So what I'm going to do now is walk through step by step how we use Kirchhoff's rules to solve, for instance, let's say what we want to know at the end of the day is the amount of current that flows through R3, okay? So let's say, how much current flows through I3. That's going to be the question we want to answer. All right, so we're going to start off by using Kirchhoff's rules. And so for Kirchhoff's rules, again, say that for the voltage around a closed loop is 0. So we need to define a couple closed loops. So I'll define one that looks like this. Okay, it'll go in this clockwise direction. So I'll call this one 1, loop 1. And I'll call this one loop 2. Okay, I could make a loop 3 actually as well, which is this bigger one. I won't do that right now. It actually turns out that won't really be necessary. We could do it, but we can actually solve the problem without doing it. All right. But if you wanted to do it on your own, that's fine too. So then we're going to say that the sum of the voltages around loop 1, this first loop here, well, that's just going to be V from, we'll start at F, so we'll go from F to A, and then from A to B, then from B to E, then from E to F. Right, and that is a closed loop because we started at F and we ended at F. And so the sum of the voltages around that loop is 0. E to F is just an ideal wire. There is no voltage drop across an ideal wire, so that's going to be 0. All right. So going from F to A, we're moving from, again, the short end of the battery to the longer end. So we're going to pick up a plus E. All right. And now what I'm going to have to do is I'm going to define the direction of the current. So I'm going to define the direction as going this way. All right. And you see here, right, that I have a junction. So for instance, I'm going to have some current flowing into B, and I'm going to have some current flowing out of B. Okay, and we're going to have to use Kirchhoff's current rule for that in a second, but I will save that for a little bit later. What I will do, though, is I'll say that I'll define the currents to go in this direction, as I've drawn here. They don't have to go in this direction. You could pick another direction, and if you, depending on the sign of our answers, you know what the real direction is. But I'll call this one into point B. We have basically 3 currents. Here, one going this way, one going that way, one going that way. So I'll call this I1, I2, and I3. Okay. We don't know what they are yet. We don't know what the relationship is until we use Kirchhoff's current rule. All right, so V from F to A was E. V from A to B, all right, what is that? Well, there's going to be a voltage drop across this resistor. As we said earlier from these sort of tips, we said, if we ever move with the current across a resistor, that's going to be a drop in the voltage. So basically that will be a minus I1 R1, right? That's what this is. The minus, again, is because we're moving with the current. And this is using Ohm's law. V is equal to IR to get this voltage drop. And then V from B to E, we kind of do a very similar thing. We say, okay, well, it's going to be a negative because I defined I2 to be flowing downwards. And the voltage drop across this resistor using Ohm's law is I2 times R2. All right. So this is using Kirchhoff's voltage rule for the first loop. And that's not enough to solve the problem, right? So what we want to know is I3, I3 is not even in here yet. We don't know what I1 is. We don't know what I2 is. So we're going to need to have some other relations. You probably remember that when you're solving some system of unknowns, you need as many equations as unknowns to get a unique solution. And that's what we're trying to do now. We're going to use Kirchhoff's voltage and current rules to get some relations by which we can use to solve for our unknowns. Okay? So now our voltage around loop 2, it's going to go this way, right? So let's say we're going to start at point B. So we're going to go from B to C, then from C to D, then from D to E, and then from E back to B. And that's going to be 0, right? Because again, it's a closed loop. We started at B and we end at B, right? So we did this. All right, so B to C and D to E, these are ideal wires. So that's pretty easy to deal with. That's just 0. So then we're left with the voltage from C to D. All right. So we can see there's an I3 flowing out of B along this wire, right? When we get to point C, whatever is flowing into point C is flowing out of point C. So that means that I3 is also the current that's flowing downwards as well, right? So V from C to D is going to be the current, using Ohm's law, I3, times the resistance, R3, and then we need to know if this is going to be positive or negative. Again, in this loop, we're going from C to D. We're going with the current, so that's going to be a negative. All right. And then we want to go from E to B. So again, the current is I2 through resistor 2, R2, and we can ask if this is going to be a plus or a minus. This is all equal to 0. Is this going to be plus or minus? Well, here, when we go from E to B, we're going against the current. So it's not going to be negative, it's going to be positive. Okay? So it's going to look like this. So we have some relationship, which is I2 R2 is going to be equal to I3 R3. All right. So we know I3. So if we solve for I3 here, we know that's going to be I2 R2 over R3. Unfortunately, we don't know what I2 is yet, right? So we still need some more information. And for that, we use Kirchhoff's current rule. So what Kirchhoff's current rule states is that the sum of all the currents into any given point is going to be 0, okay? Or in other words, the net total amount of current flowing into a point has to be equal to the total amount of current flowing out of the point, so that there's no net buildup of charge at that point. Okay, so we can see here there's for part B, for point B, there's 3 currents that are basically attached to point B or related to point B. So we have, it looks like a current I1 flowing into B, and it looks like we have I2 and I3 pointing out of B, right? The arrows are pointing away from B, and I1 is pointing into B. So what I'm going to do is I'm going to define positive as meaning flowing into point B. So we have a plus I1, right? And then a plus minus I2, because minus means it's flowing out, plus a minus I3, because again it's flowing out of point B, is equal to 0. All right, so we have I1 minus I2 minus I3 is equal to 0. In other words, what this means that I1 is equal to I2 plus I3. Okay? So now we have some relationship for these currents. We had this relationship we got before. So in this problem, right, we have three equations that we've come up with here. So I'm going to highlight the equations we've come up with as these squiggly lines, right? In other words, this is just E is equal to I1R1 plus I2R2. We have this relationship between I3 and I2, and I1, I2, and I3. In this problem, R1, R2, and R3 were given. So let's say we knew what they were. Okay, they're not unknowns in the problem. We just want to know how much current is flowing through this resistor here. Okay, so we have now three unknowns in this problem. We didn't know what I1 was, we didn't know what I2 was, and we didn't know what I3 was, right? E was given, R1, R2, and R3 were all given. So once you have, so we have three unknowns and three equations, and so probably from what you've learned about, solving systems of equations, if you have as many equations as unknowns, then you can just solve the problem. And it's very straightforward to do at this point. You can just plug it into a computer if you knew how to do it. If you've learned linear algebra, you can solve this using some matrices. But I'm just going to do it by hand. It's pretty easy. So for instance, we know that I1 is equal to I2 plus I3. So I take this first equation up here then. I know I can write E is equal to I2 plus I3. That's just I1 times R1 plus I2 R2, right? So I have now rewritten this in terms of I2s and I3s. So there's two unknowns. And then I have this equation here, which relates I3 to I2. So I'm going to solve everything in terms of I2. Once I have it in terms of I2, I can just convert it into I3 because I know what I3 is, right? So basically then I have I2 plus I2 R2 over R3 times R1 plus I2 R2. Okay. So I can group things now. So what I'll get, if I factor out all the I2s, there's an I2 on each one of these terms, I'll get something that looks like this, right? There's the first one has just an R1. There's also the R2 from this one here. And then this term here has an R2, R1 over R3. So that's equal to E. So I2, or E over this stuff in the bracket is I2. So if I want to solve for I3 now, I3 is just I2 times R2 over R3. If I clean up my algebra, I'll get something that looks a little bit like this. I'll get E R2, which comes from this term. And then this denominator here, I'll have this, if I put a 1 over R3 on each one of these terms, and there's an R3 over here, those will cancel, so I'll get something here that looks like R1, R2 plus R1, R3 plus R2, R1, or sorry, R2, R3. All right, so that's basically our answer. That's I3. All right, so that's our example. And we'll do some trickier circuits in lecture and in co-op.